So, hello everyone. I'm Ola. I'm talking to you from Newcastle upon Tyne. And as always, most of you already know the ropes. I would like to just acknowledge our sponsorship from EIS, which allows us to offer all these resources free of charge. And by resources, I mean our recorded lectures, learning tools, even virtual trips, and of course, the previous recordings of seasonal webinars. So please make sure that you will check our website. Today, let me welcome Neil Davies. Neil Davies is a lecturer in sedimentary geology at the University of Cambridge. And he has an undergraduate degree from Keele University and a PhD from University of Birmingham. And between his PhD and his present position, he was working in Belgium and in Canada. Yeah, he's a sedimentary geologist. He specialized in the field-based investigations, especially in Paleozoic non-marine strata. And right now, I'm really jealous about it. He has spent more than 40 months in the field working in, well, looking at the Archean and Pleistocene strata on almost all continents, so 6 of them. And today, he will be talking about true substrates, the inevitable preservation of human timescales, snapshots on ancient bedding plains. Last thing that I always forget and will try not to today is that during the talk, the chat will be closed. So in case if you have any question, you can just note it or write it directly, but then you will be able to post it only at the end of the talk. And remember to post it to everybody. So without further ado, Neil, the stage is yours, please.
Thanks, Ola, and thanks for coming along. Yeah, so the talk I'm going to give you today is basically discussing those bedding planes that we see in the rock record that appear to have on them features that look similar to what we might see on a modern beach or dry river bed, and discuss some of the ideas about why those might get preserved. And so, yeah, I'll jump into it. Here's a handful of other people who've been involved in many of the pieces of work that I'll go through. Right. So this image to start off with starts in a slightly different place. This is basically a Google image search for looking for an image for the geological record as a pile of books, because it's often the way we want to think about the geological record, a pile of newspapers or books in which we can read a continuous narrative of Earth history. But we know that that's not entirely true, and it's been known for a long time that's not entirely true. I mean, people as far back as Darwin were talking about how if we consider the rock record to be a book, it's a book that's a kind of tattered manuscript with many pages missing and chapters lost and individual discrete sentences all torn up and jumbled around. And that idea of this tattered manuscript is one that's taken hold of. It's been repeated lots of times. So in 1973, Ager compares the rock record to a series of newspapers, but where you only receive one every Saturdays. Other people have talked about how we just see disconnected lines and disconnected paragraphs, and they're quite hard to read. So the time and completeness of the rock record has been a preoccupation of geologists for a long time, dating back to early works such as that by Joseph Burrell, looking at early ideas about accommodation space and how changes in base level might lead to a vertical stratigraphic column preserving less time than actually passed, because only those intervals of increasing accommodation space would get inserted into the rock record. And then moving on to work in the 1970s by people like Derek Ager talking about how there's more gap than record in the rock record, and it's very time incomplete. And that intensive incompleteness of the rock record is also balanced by a kind of extensive incompleteness too, in the sense that works such as the kind of classic work by Ronov and then more recent work by Hutton and Peters have talked about how the volume of sedimentary rock changes through time. Okay, it doesn't exponentially decline in a kind of Huttonian way like people once thought, but there's certainly discrepancies in the volume of rock that's accessible for different time intervals. And this kind of incompleteness, this extensive and intensive incompleteness of the rock record impacts how much we want to, or we feel we can trust it. And I think if we want to consider how we might understand the chronicle of Earth history, we've got kind of three strings to our bow, really. One, we can look at the outcrops and the sedimentary strata that are left behind and make empirical observations of that to understand the ancient past. Or we can look at modern environments and look at actualistic processes in modern sedimentary environments, and through a kind of leap of faith, the past is the present is the key to the past, that we can interpret the ancient past that way. And we can also run more kind of model-driven understandings of the ancient past using models based on what we currently know about the laws of nature or the way in which environments work. And I think that, like, yeah, those three different approaches to the rock record should be used in unison in an ideal world. But I think there can be a perception, I think it does exist in some quarters, that the first of those aspects, the kind of empirical observations of rocks, is not as valid as it could be because it's so incomplete. Okay, and in some places you might find a very strong argument against that, saying that because the rock record is incomplete, it's unrepresentative of the geological past. But there's a problem in the sense that when we approach rocks, when we see rocks in the field, we frequently see bedding surfaces that archive information and structures that are almost near identical to those that we see in modern environments. Here's an example of some Devonian ladder ripples, and on a broadly same scale, some modern ladder ripples. And anyone who's approached the rock record, if they haven't asked it themselves, if they've been asked by a student, why out of the kind of multitude of ripples that existed, did these ones get preserved? Okay, what made it special? Because these modern ones we intuitively think are very ephemeral, that the next time the tide comes in, they'll disappear or get reworked. So why do these things get preserved? And it flies in the face, or it's kind of paradoxical to the idea of an incomplete record, that we can have these geological instants preserved so completely. And it's not just ripple marks, there are plenty of surface features that attest to short-term processes. So here are some 330 million-year-old rill marks from the Carboniferous of New Brunswick, and here are some modern ones. These are structures that you would think have got an incredibly short lifespan. So if this is a lifespan of a few hours at most, then how come this one's been archived for 300 odd million years? Other features like raindrop impressions, again, they're seemingly delicate. So what kind of processes would allow such delicate features to get interred into the rock record? Why do we have this record here of a Silurian damp afternoon in Norway, right? It's a question that's kind of dogged people for a while, and many suggestions have been put forward. I'm running through a few of these little slides at the beginning just as examples. These are some drip impressions from foliage in the Carboniferous of Eastern Canada. And here's some modern drip impressions. Again, very similar features, very analogous. Again, things that we would think are ephemeral and should disappear. And even features like these adhesion marks, these ones from the Silurian of Western Australia, and these modern ones, really delicate features, even in sand, formed by wind-blown sand adhering to damp sediment through the kind of interstitial water between grains. How on earth has that been preserved for 400 million years when something like this seems so unresistant to destruction? All of these features I've talked about so far are examples of what we're going to call true substrates. Okay, so true substrates we're considering to be bedding planes that archive sedimentary structures or information that shows that they demonstrably existed at the either the sediment water interface or the sediment air interface, depending on what environment they were deposited. So this is the image from the title slide, showing some Silurian ripples here grading into some modern ripples, just with a Photoshop. So what we want to ask is how these things enter into the rock record and what they might mean for our understanding of Earth history as these snippets of apparent truth in a very incomplete record. these are questions that are particularly important from a kind of paleoecological standpoint, because while in sedimentology we might find adhesion marks or find ripples or find rill marks and add them to our kind of shopping list of sedimentary structures for interpreting a given set of facies, in many instances of trying to understand paleontological or paleoecological features, it's the structures themselves on the true substrates that are directly of interest. Okay, and so questioning exactly why they are there often leads to special explanations relating to the taphonomic conditions at the time of their interment. But many of these features fundamentally really aren't that much different. There's not much difference between an arthropod trackway and an adhesion ripple in terms of preservation, or a burrow opening and a rill mark. You know, these things should be seen as comparable and therefore might share a common explanation. So the slide has jammed. Oh, there we go. Right. In terms of explaining preservation from of these features in the past, a number of different explanations have been put forward. On the one hand, you might explain things through, say, special pleading to taphonomy, special conditions that might have strengthened or hardened a substrate, or otherwise caused a substrate not to be eroded. So questions about whether or not the chemistry at a certain time was different, the ocean or air chemistry was different, or whether you had things like microbial mats binding the surface. That's the particular kind of thing that people would discuss for certain kind of soft-bodied impressions in ediacaran strata. Other explanations have been related to exceptional sedimentation, that in order to see these small delicate features being preserved, they must have been interred very rapidly and very efficiently by a thick pile of sediment that stopped them from being eroded away. And a third kind of avenue to approach these structures in the past has been just outright denial. Okay, and a good example of that comes here from the idea of raindrop imprints. So there's a mid-19th century spat between Charles Lyell and William Buckland about whether or not you can get raindrop impressions preserved in the rock record. Lyell says you can, because he's seen them in the rock record and he's seen modern examples and compared and contrasted them. Buckland denies this is possible. And that argument about raindrop imprints has gone on for quite a long time, periodically re-emerging, to the extent that you'll find textbooks today that say it is unlikely that you'll find raindrop impressions in the rock record. But I say I'm on Team Lyell there, you certainly do. And there's features in the rock record. These are snippets of statements that have been made about certain sedimentary structures. This is these features here are these kind of shadow features on a beach that have been caused in this instance by wind blowing across and leaving these kind of sand shadows behind obstacles. There are papers that have said that these features, known as settles, are only known in the Precambrian, Cambrian, and modern, and therefore they must have been protected by microbial mats that went extinct for a long period of time, and therefore went extinct, and therefore or were grazed away, and therefore they're not being preserved throughout the whole of the rock record. These are just two examples of Silurian examples of settles, which shows that's not true. And I think the point there is to make the statement that if you're looking at features in the rock record, it's very important not to be restricted by your own experience. You know, you can't speak for certainty about the whole rock record. Likewise, we shouldn't get too caught up in what we think should or shouldn't happen. These are different statements about how likely adhesion marks are to appear in the rock record. The transition of adhesion ripples to a fossil condition is unlikely. Preservation potential of adhesion marks is low, and yet they exist in the rock record. Okay, here's an example of a true substrate from the Silurian of Western Australia, again showing the margin of the puddle with adhesion marks here, a small bit of adhesion mark sediment that slipped into the puddle flank, and the ripple marks on the bottom of the puddle. And there's a modern example showing exactly the same kind of thing happening. So we have to be cautious about, you know, just what we've experienced in the rock record. And in this talk, I want to go through a number of different aspects about true substrates that I would like to suggest are true. Firstly, that true substrates are an inevitable byproduct of the way in which the sedimentary record accrues. Secondly, None of them require any special taphonomic conditions for their preservation. Thirdly, we're likely to encounter them at outcrop, and they're going to be naturally common. And between these different aspects suggest that we should perhaps not discount the sedimentary record and empirical observations of the sedimentary record just because we consider it to be a tattered manuscript, because those tatters can actually hold very faithful archives of history and be representative of the geological past. So the first thing to talk about as we consider these is where these features occur, because it's important that true substrates occur on bedding planes, such as these dune bed forms here on a bedding plane in the Cambrian at Brittany. We don't see many of these superficial features in vertical sections, but again, obviously, we can see bedding contacts as these vertical expressions of bedding planes. Now, the common definition of what a bedding plane is that there's an abrupt change in the depositional conditions that have terminated the preserved record of any kind of antecedent bed beneath there. And I think it's very important at this stage to emphasize that when we talk about an abrupt change, we're talking about a material change in the rock, rather than anything that implies something catastrophic or anything that implies something even sudden. Okay, it's just an abrupt change in the material properties of the sediment pile. And we can think about how bedding planes form with reference to the different sedimentation states that may exist in a system at a time. Now, this concept of sedimentation states from this paper by Tipper in 2015 is a useful one. This paper was looking at the kind of states you might plug into a model for generating a numerical stratigraphy or a synthetic stratigraphy. And the idea being that at any point in that model, you would see erosion, a kind of deletion of the rock record, in which case the lithic surface is taken up and removed, transport, in which case there's kind of bypass of that surface, deposition, in which you're kind of recording the sedimentary record and adding sediment and raising the lithic pile up. Or, and this is important, this notion of stasis, whereby nothing's actually happening. Okay, and Tipper's kind of championing of this idea of stasis has been influential in it and is certainly useful, because stasis is something we do see in modern environments. Tipper's ideas were applied to a point, a Euclidean point. In this talk, I'm distorting it somewhat to talk about a small patch, maybe like a bedding plane or so on, because I think for understanding the way the rock record's built up, we do need to do that. And we can then think that any bedding surface is going to develop if we see changes between these different states, or we see changes in the intensity of one of these states. And I'll come back to that in a second. Another key point to make at this stage is that Tipper's idea of stasis, while useful in terms of numerical synthetic stratigraphy, Tipper considered that nothing happened during stasis and therefore nothing is recorded. And I think that's one thing we do want to explicitly move away from in this particular talk, because it's precisely during these intervals of stasis that many of these signatures of true substrates get imparted. It's when there's not active deposition or active erosion that we see features forming. So whether or not it's these kind of defunct ripple marks at the end of the kind of migration of the sand body, or the arthropod trackways crawling over the top of it, these are the signatures that are telling us that this surface here was once part of the surface of the sedimentary environment. So we'll move away from that aspect, but we'll retain these ideas of deposition, erosion, stasis, and stasis to show how different types of bedding planes can form, because not all bedding planes are alike. Okay? They don't all have the same formative mechanism. They all have the same formative mechanism in the sense that there's a shift in sedimentation state, but they can be quite variable. And this little cartoon here is just showing a sequence of events that might be bookended by deposition, in which something different happens, or some sequence of kind of compound sedimentation states happen in between, and how they might lead to different signatures and different types of structure behind. You'll see these two that have been I've highlighted with a little asterisk. Those are instances where we might expect to see true substrates occurring. In other instances, we might not expect to see such features. The real world examples of those kind of cartoon examples I showed on the previous slide are shown here. Here's a sample, here's a selection. This is a bedding plane here, where we've seen evidence of deposition followed by an interval of erosion that's caused this kind of channel scour, and then further deposition on top. So if you were to go to this bedding surface here, you're unlikely to see any features that show that it was ever a true substrate, because in fact it never was. It's an internal artifact of the sediment pile that's formed because it was filled in almost instantaneously after it was cut. Other instances might be these surfaces here of forceps inside cross bedding, which we could consider to be deposition bedding planes, in the sense that there's been a fluctuation in the intensity of deposition, but it's never really ceased long enough for stasis to take hold long enough. And then finally, we have these true substrates where the deposition has seen an intermittent interval of stasis where nothing has happened, and to preserve some kind of signature. For the sake of completeness, we should also account for the fact that some other bedding planes are not related to these fluctuations in sedimentation state. Some might be just kind of palimpsested messes like this one here, where we see some ripples, some desiccation cracks. It's a kind of melange of different intervals of time because of the way the rock is broken. Other ones might be wholly kind of non-genetic, like this surface where the modern erosion of the bedding plane has revealed the kind of calcary horizon inside there. So we know it's deeper in the actual substrate. Other things might be examples of kind of splits along facility and so on, maybe in mudstones. But these are the ones we're interested in, and particularly this kind of genetic bedding plane where we're seeing evidence of stasis. We can consider these different kinds of bedding plane when we look at an outcrop. This is a rock outcrop in the Silurian of Northern Australia, an aeolian and aeolian interdune succession. And we can see small dune toe sets there. We can see maybe some kind of interdune facies. But by splitting it up and looking at the different meanings of the bedding planes inside there, and seeing that there are some bedding planes that are true substrates, revealing evidence of stasis, some which would never exist at the time of deposition because they are erosional features that were subsequently filled in by deposition, and some which are like the forceps of dunes, which are just these instantaneous fleeting fluctuations in deposition. We can kind of build up a picture here that we've got the rock record is more complicated than we think, right? It's not, there are holes inside it, but there are little pockets of completeness hidden inside it as well. And to consider how frequently we might expect to see such evidence for stasis and true substrates, here's a small little case study from the Tumblagooda sandstone in Western Australia. This is facies 3 of the formation. It's an estuarine kind of facies association with many kind of estuarine dunes inside there, and it contains a number of trace fossils. This is what it looks like close up. We've got lots of cross-bedded sands on top of one another, making some small cliffs around here. And then these big kind of wave-cut platforms reveal these kind of cut-throughs, these kind of horizontal slices through cross-bed sets. Very similar to kind of the models of Almond and others, where you'd expect to see these truncated features, okay, being effectively an erosional substrate inside the sediment pile. That facies association contains a lot of different trace fossils, or a lot of trace fossils, though, mostly of this one kind, Samachnites, which are these small raised levees with a line down the middle that probably reflect a kind of mollusk-like organism, shallow feeding underneath the substrate with its siphon sticking out the top. So these are surface features on the sediment surface on a substrate. The problem is that where we see these is in locations like this. So if we look at one of these kind of truncated dunes and zoom in, here are some of the truncated forceps forming these lines across, and you can see the whole surface is riddled with these intricate kind of Samachnites traces. In other words, what must have happened is that as the dunes were deposited, or after the dunes were deposited, they must first have been erosionally truncated and then colonized by these surficial trails before being interred again. In other words, we have to have seen deposition followed by erosion, followed by stasis, followed by deposition that wasn't without erosion. So that latter stage of deposition did not remove these traces. And to show just how improbable some of these things are, these kind of DESD surfaces, some of those sedimentary traces underlie these kind of gravel lags. So gravel lags that you would instinctively say were high energy or higher energy deposits, and yet they're deposited without having eroded these sedimentary traces below. Now these DESD type true substrates are more common than you think if you look. Here are other examples of where we see these kind of traces in unexpected places that tell us that there must have been stasis following an episode of erosion. An example here of some volcaniclastic flutes or grooves from the Borrowdale volcanics in Cumbria, in which we can see diplectinites trackways going up and down over the top. Now, you would instinctively think if these trackways weren't there, that this flute may have been cast almost instantaneously by the overlying sediment, but this shows that it wasn't. And likewise, this is the base of a turbidite, again, showing evidence of event separation, because we're seeing these kind of graphoglyptid traces that come up and down. This is the flutes on the base of a bed. So the flutes must have been cast, then colonized, and then the next layer must have been deposited on top. And we see other evidence as well. It's not just based on technology. Instances such as this kind of scoop-shaped puddle, an erosional kind of puddle, again from the Moridi sandstone in the Northern Territory. In this instance, we've got ripple marks forming in it, showing that there must have been an erosive little puddle that saw the formation of ripple marks after it had been eroded and prior to it having more sediment deposited on top. Or this example here of a kind of scour hollow picked out here by these white lines around a standing calamites plant in the Carboniferous, where there are, if you just pick out here, lots of little kind of drip impressions and adhesion marks in that actual scour hollow itself. Again, showing that this erosion of the scour hollow must have formed, and then there was an interval where it just stayed as that erosive bed form before that erosive substrate before it was cast by the subsequent layer of sediment. So true substrates are kind of indicative of this event separation that we don't often pick out in the rock record, but it appears to be in many places. And there's no reason why to think that's unusual, because we see it in modern environments too. So here are some modern sand dunes where we can see that we've just got this kind of erosive truncation of some of the former kind of forceps of that dune from a previous time. So if we were to walk over the top of that and it gets interred in the rock record, then we'd see it in true substrate with this kind of deposition, erosion, stasis, deposition history. Now this suggests that we can see these things in the rock record, but it brings some questions about exactly why we do. Why did we see those tumbler Gouda traces underneath a kind of gravel land? And the kind of traditional view about some of the ways in which trace fossils in particular might get preserved, is kind of the older Stylacrian view, is this idea that we would have to have stabilization of some form in order for those footprints or trackways to get preserved. We'd have to harden the sediment, otherwise it would get eroded by the subsequent deposition of the next layer. And part of that argument lies on this kind of intuitive reasoning that if we walk on a beach, our footprints disappear when the tide comes in. But even that might be a bit oversimplistic. And this is an example, again, just a modern case study to illustrate a point, from the Bay of Fundy in this instance in New Brunswick, where the bay with the world's highest tidal range sees 4 million cubic meters per second of tidal flow every day, which is greater than the total outflow of all the world's rivers. So this is an area where the tide coming in and going out is a very powerful force, which you'd expect to be erosive. But at a location like this at Hopewell Rocks, you can wander down as a tourist attraction, and there are signs saying keep off the keep inside this restricted area, keep off the mudflats, and no one does. And if you walk there, you'll see there are plenty of footprints in the actual mudflats there. And instinctively, you'd think that those were footprints left by people from the same tidal cycle that you're visiting. But if you look in those footprints, what you'll often see is they're actually fully colonized by little gastropods. Little gastropods that are using these little seawater-filled footprints as the last kind of hollows where the seawater is retained once the tide goes out. In other words, those footprints were there prior to the previous tide coming in and going out. Okay, so we see a number of these different features, and just a very impromptu kind of testing of that. This is elsewhere in the Bay of Fundy on the Nova Scotia side, where on the 8th of September 2018, we drew into the sediment there, we walked out, made some unusual footprints and scratched the date in the rock, came back 2 days later, and the footprints were still there. Also, so was some of the writing. So this is what we wrote before, Saturday the 9th. There's still an S preserved there. So things can survive unlikely lengths of time. And you'd be justified in this instance of saying, well, this is muddy sediment and the cohesive effects of the sediment are going to play a role. And that is absolutely true, but it's not the only part of the story. And we can see just even on kind of sandy beaches around the UK, we see instances where substrates are being interred or disinterred by sediment. So this is just an example. Here we've got some wet sand where you've got a little, a small little patch of windblown sand, which is clearly interring some of the adhesion marks and footprints that have been left behind on the beach. And this is an example here, which is probably more interesting but hard to explain, looking down on the toe of a kind of nebka on a beach, which on the day this photo was taken was very windy, and this little patch of sediment was being blown away by the wind and disinterring what you can see underneath, a series of ripples from before this sediment was deposited. Okay, so here's an instance where you can see the beach surface on that day is very flat, but as this little nebka of sediment retreated, it revealed the ripples that it had been laid down on top of. So the effect there is, yeah, true substrates can be preserved without having strengthened sediment. And we can kind of visualize that a little bit better with this kind of conceptual model of a pair of scales, where we can think about the fact that whether or not we see a substrate being eroded or not is kind of a balance between not just the erosion resisting forces where many previous explanations have lain, but also the erosion driving forces. In other words, we can have kind of relatively low erosion resisting forces, but if the erosion driving forces are lower, we'll still tip the scales in favor of preserving a true substrate. So we can think there's these two scenarios where we could see a scenario where the forces that would resist erosion outweigh the forces that would induce erosion, and vice versa. And what we're interested in is wondering how frequently this situation where the resistance of erosion outweighs the erosion driving forces, how often does that occur in the rock record or in sedimentary environments in general? And the way we can tip the balance scale is by increasing things like substrate shear strength. So clearly things like cohesion and adhesion and interlocking of grains do play a role. Hardening of sediment can play a role, but we can also just have weak fluids that are deposited from the next layer of sediment. So how often does it happen that we see that tipped balance? Well, firstly, we need to recognize that the frequency of times we'll see erosion resistant forces outcompete or outweighing erosion inducing forces will increase with time. Okay, so if we run the same experiment again and again and again, sometimes that scenario will be met. And that's the one thing that sedimentary rock outcrops give us, is the fact that we have a time-rich kind of sample with many kind of dice rolls to try and achieve this in a small spatial area. And this is an example from the Tumberguda sandstone in Australia, where in this section alone, there are about 30 different things you could class as a true substrate, but that's out of about 500 or more different kind of bedding contacts that do exist there. Okay, so yeah, we kind of get biased to the fact that the true substrates are more interesting, but in actual fact, one of the reasons we might be seeing them is simply because they do rarely occur. They rarely occur, and if we're doing this, if we're seeing multiple layers of sediment being deposited, sometimes we capture instances of that because we're seeing more kind of dice roll for more time. Another factor that comes into play is that we'd expect to see that scenario more frequently if we increase the spatial area that we consider. So this is let's go back to the Bay of Fundy. This is the Bay of Fundy here. And we can think that even though it's got this incredibly strong kind of tidal discharge, it's not the case that every time the tide comes in, all of the sediment and all of the substrates across this whole area move, nor is it the case that none of them move. Okay, but it's a much more spatially patchy process, which is why we see things like dunes and rivulets when we zoom in on part of it. And the key thing here is that if we consider that the potential for preserving true substrates increases if we increase our spatial area, we have to also then consider that the spatial area we normally approach from an individual bedding plane is really, really quite restricted in the scope of a wider environment, which is something I'll get onto in a second. But just for the case of scale, this image here is approximately this area on this Google satellite image, and this image is approximately this area on this Google satellite image. And these two little lines here showing X and Y are just two examples of two very large or impressive kind of true substrates in the rock record. Okay, they're small samplings of a much wider hidden area. So why does that play a role? Well, if we go back to those kind of substrates from the Tumbleweed sandstone, here are our Samic gneiss traces on the truncated faucets. This is a scale of the truncated faucets within the wider kind of fascies environment, and then within the wider kind of environment of deposition at the time, maybe some kind of estuarine bar. Now, because these outcrops we're seeing are capturing only part of the wider environment, we shouldn't be unsurprised that we see snippets that have been preserved in their entirety. A way of looking at this is to consider a sedimentary environment, which is just represented here in plan view as a kind of a box. And within that wider sedimentary environment, here are three locations which are destined, for whatever reason, to be outcrops in the future. If we subject that sedimentary environment to some kind of flow event, in this instance, one that's dissipating its energy radially, then we'll see that different parts of that sedimentary environment are affected by erosion, stasis, or deposition, because as the flow dissipates energy radially, it drops below a number of different critical thresholds for moving sediment. And so the net effect of that is that in this wide sedimentary environment, we will see parts of the sediment, the lithic surface that have been eroded, parts that have been buried and raised up, and other parts where nothing has happened. And then if we subject that environment to a second episode of, or a second kind of depositional event with a slightly different inception point, then we'll see more erosion, more deposition, and more kind of stasis, but it will be in a slightly different location, which means that each individual point within this environment will have seen a different kind of history across those 4 time intervals, and the different outcrops we see will see different records. In other words, this new map of this environment there shows that it's not just a simple case of erosion and deposition and stasis, but rather a suite of different potential compound sedimentation states that have occurred, some of which have the potential to leave behind kind of true substrates, and shown here in a kind of graphic log kind of form, and some of which may have been captured by these future outcrops for that particular interval of time. So that's a little conceptual model. A kind of real world example of that could just be seen here. These are a couple of images taken from the same spot of a beach in northern Scotland, again a sandy beach with no real cohesion to the sediment. One taken one afternoon in September last year, the other one taken 2 days later, after a couple of tidal cycles under which the beach was submerged, and also after a kind of a storm event. What we see is that we can see areas in there where we've seen deposition during that time interval, but we also see areas where parts of the beach have been eroded, and critically, we see parts of the beach where nothing has happened, despite the fact it's been submerged by water. So the point is that erosion, deposition, and stasis can all be spatially patchy on a small scale, and so sometimes we're going to capture these kind of snippets of true substrates. And I think a useful place to use a couple of the diagrams to consider in this regard here are this diagram here from Andrew Mile and this one from Martin Kleinens. Mile's diagram here basically suggests that there are the smaller the kind of bed form or geological feature you're looking at, the faster it tends to form. Okay, and individually at the point of its inception, we can consider that some of those features have got very limited preservation potential. Okay, so an individual ripple that you see on a beach has got an extremely low preservation potential compared to, say, an entire basin fill, which is much larger. So it has a higher preservation potential. We'll come back to that in a second. Likewise, this diagram here from Martin Kleinens talks about how many features or many processes, geological processes that might leave sedimentary signatures tend to show a relationship between the time scale and the length scale of the phenomena involved. In other words, the smallest features, the smallest processes tend to happen much more quickly. What's important is that when we, if we consider that the length scale is important for discretizing our view to seeing very rapid time processes, then when we look at natural rock outcrops, we're naturally looking at a relatively spatially restricted area. So the spatial scale of many rock outcrops is small. Here's some people for scale, and here's a kind of typical kind of coastal rock outcrop. We struggle sometimes to work out what the timescales are involved in the deposition of sediment because we lack the kind of stratigraphic precision to really pick out what's going on there. But in this particular instance, we've got a helping hand from the fact that much of it is made up of tidal rivenites that we can count up and say that actually effectively half a meter here is approximately 84 days of sedimentation, with very few days missing in between that continuous sedimentation. We can count up spring and neap packages inside there. But we can see that some of these spring and neap packages have been colonized by burrowing organisms. Crucially, this particular package also reveals evidence for a number of true substrates along on the top of some of those tidal laminae. And we see those true substrates in the form of these burrowed surfaces, which we can infer aren't palimpsested, because one, they're very equally spaced and equally spaced, suggesting that organisms weren't competing each other. And secondly, they're all surrounded by a rim of the sediment that the burrows excavated. So there are pockets inside this high resolution pile of sediment, high temporal resolution pile of sediment, that give us very high kind of paleoecological resolution, because we're effectively seeing exactly what was happening on that particular small patch of bedding plane during a 6-hour period, effectively. And the reason we don't see palimpsesting inside there again is a kind of trick of the fact that the outcrop is really just showing us part of the environment there, and not every single rivemite layer is colonized by burrowing organisms, simply because those patches of burrowing organisms were randomly distributed inside the wider sedimentary environment. So only occasionally did a burrowing patch intersect with the sample that we're seeing in this vertical profile of a suite of different true substrates. So this is important then. Small outcrops and outcrops in general and small bedding planes naturally discretize our kind of spatiotemporal view to the smallest scales. So often to processes that are happening on hours to days to weeks to months, rather than longer term intervals. So we get some very high resolution snapshots of what's happened in Earth history. This diagram here is a kind of modification of the kind of Kleinens diagram, showing that we can kind of consider the time length scale of bedding planes or outcrops and understand that true substrates capture these small time scale phenomena at very small length scales. Things that normally coincide with the kind of timescales of our own human experience of walking on the beach and seeing features. Additionally, these kind of what we're capturing at outcrop and capturing bedding planes are small fractions of sedimentary or geomorphic elements that are bigger than the outcrops themselves. Okay, so an outcrop can only capture part of a sedimentary geomorphic element if it's bigger than the outcrop itself, or it can capture perhaps an area of heightened local accommodation between two such kind of large elements, such as was the case there in that Northumberland example, where those tidal ribmites were likely in some kind of interdistributary bay. And that means you can revisit Miles' little diagram here and say that yes, these kind of small scale features have a low probability of preservation at their point of creation, but because their populations are so great, we actually see a lot of them in the rock record, and also because they are internal components of these kind of different order features. In other words, you can't have a basin fill that's not filled with larger sedimentary elements that are also composed of these very small scale features. So altogether, this means that our probability of seeing the kind of true substrate in an individual outcrop is very, very high. Okay? And so we can then say that true substrates do sample these kind of, and outcrops sample these kind of experience scale sedimentary processes. They appear to be this inevitable byproduct of the accrual of the sedimentary rock record, because deposition and erosion are not totally efficient everywhere at all times. And therefore, they require no special taphonomic explanation for when we see them. They are naturally common outcrop, and they give us these faithful records of the kind of day-to-day mundane norm from a particular environment at any given time period. And that means that the way the rock record's built up is by these individual building blocks that are faithful records, even if the record as a whole is incomplete. And the reason that's important, well, it's important for a couple of ways. Firstly, those building blocks are as complete as they can be, irrespective of their age. In other words, an emergent ripple in the near approach of Scotland is comparable with a modern or a Silurian emergent ripple, but we can see some differences inside there. The time incompleteness of the record doesn't mean that we're looking at a flawed record, but lots of these multiple faithful records that we can compare trends between. So, for example, in this emergent ripple here, we see no evidence of, say, trackway inside there, but here on this Silurian one from Norway, we can see evidence that by the time these ripples were formed, we were seeing some evidence of animals crawling over emergent substrates. Likewise, examples here, for example, these are modern kind of soft-bodied animals. Here's some ediacaran animals, and there's a Silurian one. Okay, you know, just because we're seeing these different samples are samples of individual time intervals, and even though there's variable rock volume per time interval, that just means we're seeing different sample sizes rather than they being intrinsically flawed individually or needing special explanation. And that means that if we can see trends in the global picture from a multitude of individual case studies, we can't discard those trends as artifacts of an incomplete record. Okay, so in the instance of trackways appearing in emergent substrates towards in the Silurian, perhaps, then we can say that the fact we don't see trackways in emergent or in non-marine substrates much older implies that's a genuine trend. Okay, because each individual sample should be taken as a faithful representation, and it means that ultimately we can go back to these ideas about how the rock record is an incomplete book, but the rock record's more of a telephone directory than it is a novel. In other words, we can find little snippets inside there that contain all the inherent information that they would ever have contained, like a name and a number inside there. And by looking at trends in those little snippets and fragments that we've got, we can pick out trends. We know there's no one with a surname beginning with A at the end of the telephone directory and so on. So we should trust those little samples, and we shouldn't assume that the incompleteness of the rock record is a reason to wholly ditch these kind of empirical observations of individual samples. Yeah, so any questions? And that was it.
Neil, thank you very much for this absolutely amazing talk. I have to admit, I really enjoyed this small experiment that you have showed with writing on a mud plane. And it's so simple and like so informative. and the pictures of your outcrops, really fabulous. Thank you very much. The chat is right now open for questions. And I see that there are already some questions in the chat. Please remember to write to everybody and to write where you are watching us from. Niels, are you ready?
Yep.
Okay, here comes the first question from Yakov from Wales. Neil, this was even more fascinating than your papers. Question: how long does a surface need to be non-depositional and non-erosional before you would label it as a stasis? Second, minutes, days, see you in the upper grid sometime.
Yeah, I think it depends on what you're trying to understand the meaning of the surface. I mean, many of the features I've given are examples where it's ichnology that's showing the level of stasis inside there. So I think you just need to take a pragmatic approach to this. That it's going to be very different in different locations. Sure, you could say you can discretize this to like just individual grains and say that stasis might last for a nanosecond, but I think it's useful for us to consider practically that there are some intervals where clearly stuff has happened and it's had chance for stasis to occur. And there's certainly also obviously instances where stasis is much more prolonged, and maybe we start seeing things like geochemical profiles developing inside substrates and paleosols and so on. So I think it's very kind of case by case basis for how long you'd consider stasis to be, depending on the purpose of the study. The fact is that it does exist in there in some way, and it will be different in different environments as well. The aberrative grits will see potentially 10,000 years of stasis in between there, but you might see in a tidal environment 6 hours, like those ones in Northumberland. So it can be different, I guess.
Claire from, I don't know yet where, but I'm sure you'll find it out later. So Claire says, Newcastle. Oh, my neighbor. I will try again. Claire writes, cool talk, Neil. Do you think there's any link between grain size, bioturbation, and preservation? Commonly, we see finer, muddier substrates between highly bioturbated in modern estuarine settings, and they appear less affected by tides compared to tidal sand dunes. I'm guessing stasis is in these settings could also be localized to each facies. In example, tidal flats, mud flats, and sand flats.
Yeah, I think that's almost certainly true, that different parts of the environment are going to see different levels of stasis. If you go to a coastal system that's got a multitude of different kind of sediment types, the sand's obviously going to be much more frequently mobile than some of the muddier sediments inside there too. So yeah, there's going to be some kind of story inside there. Also, perhaps if you've got a setting where you've got prolonged kind of stasis, you might expect to see more palimpsestic in some instances. So it becomes hard to say something is a kind of true substrate or everything was contemporaneous with one another. But yeah, certainly I think even you can move this down to even smaller scales and say that different parts of different environments are going to be more likely to experience stasis. Not just in a tidal environment, but in a river environment, you're more likely to see evidence of stasis on those kind of the margins, the fluvial floodplains, rather than the channel itself, where there might be more frequent movement of sediment.
All right, thank you. Next question is from Valentin from Oslo. Such a cool talk, Neil, and I agree with Jaco here, so fascinating. My question, I have to admit, I agree too, absolutely. My question, in your outcrop from the Northern Territory, where you measured circa 500 bedding planes and circa 30 true substrates, TS, were these true substrates randomly distributed or more grouped together, which may reflect some changes in climate or anything other than change? I'm sorry.
Yeah, I mean, there were small groupings inside there, and I don't think it's entirely random. I think it's the same as the last question, basically, where you were seeing pockets where you would move through a whole suite of surfaces that didn't have true substrates in there, they tended to be, if you looked at them, maybe more low angle inclined bed forms, basically, that were probably moving too quickly, or probably we were seeing more deposition inside there. So yeah, it was effectively wherever you were moving away from, I guess, effectively wherever you're moving away from the loci of active energy and deposition in the system, you're more likely to see true substrates. But there's got to be a sweet spot in there where you have to have more deposition afterwards. So I think, yeah, the shifts inside there were more likely controlled by local fascies than anything on a broader scale. But I guess if you were going to look at things like, that's what I'm saying, I'm thinking we're looking really at kind of short-term, day-to-day kind of trends or month-to-month trends. So discretizing our view to that kind of scale means we're not seeing many, we're not seeing climate change inside there. But if you were maybe to take these kind of concepts and switch them out to looking at things like longer-term things like geochemical profiles or paleosols, I'm sure that there might be bigger trends in that kind of thing. So you need to, I guess, extend the view to a basin rather than an outcrop.
So I will just use Valentine's question to squeeze here my own one, which is a little bit related. Did you ever encounter true substrates which were kind of cyclical in an outcrop?
Well, I guess, I mean, though, yeah, part of it is trying to determine what a true substrate is. Those examples from Northumberland, those tidal examples, they clearly are cyclic. They're showing some kind of tidal cyclicity inside there. But the ones that you could identify as being true substrates were randomly distributed inside there because they're the ones that you could see. There were burrow tops inside there, burrow tops on the tops of them. So yeah, it's more, yeah. I guess it's, yeah, it's, there's a bias to what you can actually pick out inside it. I think, yeah, the use of these is more not for looking for cycles, but more being appreciating just how some of the features you see are just kind of like mundane day-to-day processes, and give us nice little snapshots of days in Earth's history.
I guess it's also what you mentioned at the talk, that sometimes it's simply a kind of pure luck or chance that we find these true substrates because of the heterogeneity, how they are preserved. So yeah. No. All right, thank you very much. I will just proceed with the questions from the audience. So Ross from Queen University in Canada is asking, so first he's telling intriguing talk. Thank you, Neil. And here comes the question. Could one consider applying the relative abundances of true substrates and how it varies in the sequence stratigraphic studies? So yeah, I guess this is also the question in the same direction as the ones before.
Yeah, and again, I guess that, you know, because you're looking at, say, if you're seeing more of these true substrates in areas where you're not seeing kind of focused erosion and deposition very frequently, then there'll be certain parts of certain environments that in different systems tracks where you would expect to see more or less true substrates being preserved. So I think, yeah, there is, but yeah, exactly where those are, I guess it's overridden by what the environments of deposition are as well.
Next question comes from Gary from London. Thanks, Neil, for a really thought-provoking talk. If I understand correctly, we should expect to see many more true substrates for small geomorphic elements, example ripples, than for large geomorphic elements, example dunes, in a particular environment. Has this been tested statistically?
No, but I think that part of the reason as well is that it's more about the scale at which you can access these different features. You can find a very small bedding plane that's large enough to encapsulate very small features inside there that are very intricate and so on, and the kind of thing that someone picks up and takes home to put a mantelpiece or a museum. But those are going to capture these smaller scale features. I think part of the thing that would skew statistical tests to this is the fact that it's hard to quantify the scale of an outcrop that you're actually taking these observations from. So there are clearly some kind of instances where you're getting kind of small scale dune features being preserved, but there's that skew to the actual the collection and what outcrops can access, I guess.
Oh yeah, there's another question just popped in. Yeah, Gary said thanks, and Diana from Argentina says, thanks for the talk, Neil. What do you think about the role of microbial mats in preservation of true substrates, such as ripple marks?
Yeah, I think that you can, obviously there's plenty of evidence that microbial mats can stabilize sediment and cause ripple marks to get preserved and cause substrates not to be eroded. So they're one of those aspects in the balance that strengthen sediment and are going to promote the resistance to erosion. So microbial mats certainly promote preservation of ripples, but on the other hand, ripples don't necessarily need microbial mats to be preserved, I think is that's the view I'd take.
Legion from China says, very interesting talk, giving us a new window to see the old rocks with fresh ideas. My question, how did you identify different substrate in the ancient rocks, comparing to the modern sediments?
Yeah, I mean, basically that's it. Yeah, the features that you'll see inside there often have modern analog. Some features, I guess, don't. There's plenty of instances where you can find rippled surfaces that have on them unusual kind of blobs or circles or shapes that don't seem to have an intuitive reason behind them. But generally, yeah, just look, this wasn't one project. There's a whole host of different localities and environments, and yeah, they're just examples that have been cherry picked from that succession and compared with photos from modern beaches.
This was a really good question. I also wanted to ask you, like, how does it look like in, let's say, Archean or Paleozoic rocks when the environment was so much different, and probably you cannot really find a very good equivalent. So does it happen to you often to find a true substrate or you think that is a true substrate, but you can't really find a modern equivalent for it?
Yeah, I think there's probably a few little, but in those instances, it's probably mostly going to be something. Well, there's got to be a simple explanation. So it's something biological maybe that can't really be described particularly well. So yeah, there's a whole host of different features that are kind of problematic to understand or interpret. And you wouldn't like to come down on one side of an argument or another. I think the key thing is though that, yeah, in terms of the biological structures, I think to say there are the appearance or disappearance of certain features or fascies or true substrates should be taken as being genuine because the samples themselves, any collection of different substrates or outcrops or samples is a valid sample for a given time interval.
Here's the next question from Daryl from Canada. Neil, your example seems to indicate a greater preservation of these structures in the tide influence environments. Do you think preservation would be greater in estuarine setting than in lakes?
Yeah, a lot. Not entirely. I think a lot of the examples that I've used, some of them are from tidal environments. There were some from kind of aeolian environments and a few from fluvial environments too. The modern examples are mostly from beaches because they're the ones where it's easier to photograph them. So I think there's a bias towards what we can see for comparison for the purposes here. There's no reason why there wouldn't be true substrates from lakes. I'm only a little thumbnail at the moment. This is a big rock, but there's a series of fish trails on a lacustrine sediment surface, which are probably not visible from the Carboniferous of Cornwall. So I think, yeah, you'll be able to find these things in any environment where there's going to be some form of prolonged stasis. Yeah. But the problem with lacustrine environments, I guess, and with some other emergent ones, is that sometimes you're going to get kind of palimpsesting of features if you've got, for example, desiccation, deep desiccation that affects these kind of these strata. So especially like shallow lakes, there might be some issues inside that.
Neil, it appears you were very well prepared for a question like this with a hand specimen, like a rather larger hand specimen to demonstrate. Yes, at the moment there are no, oh yeah, there is a new question. More new questions in chat. All right, so Jakob is still from Wales. Have another question. Would you expect true substrates to be more common in environments subjected to episodic sedimentation erosion like the continental margin?
I think, yeah, certainly those environments where you've got a prolonged interval of stasis, and then you've got that means for casting by an overlying flow that might be losing its energy as it's moving along, are very good for preserving true substrates, because in those instances you don't necessarily need to have the sediment strengthened. You just got a weak layer of sediment effectively settling out over the top of it. But again, that's the kind of thing you can see also in some lacustrine kind of turbidite type settings as well, or you can see in parts of tidal or shallow marine or fluvial environments as well. There are pockets. There's certainly going to be a much larger area of those true substrates available in the deeper water, but that's probably a facet of, yeah, the scale of these features being larger as you go offshore, I guess.
And Valentin has another question. Are true substrate then only being preserved in silicic-clastic successions?
I strongly suspect not, but there's definitely a bias towards what I've looked at. So yeah, it requires more people to go out and look at these things in carbonate settings. I haven't been to enough actively forming carbonate environments to know what kind of things to expect.
Yes. Dear audience, don't be shy. If you have another question, just type it, please. So just in the meanwhile, what is your favorite of all times true substrate, if you have a favorite? I guess it's probably not a very fair question, but who knows, maybe you do.
Structure-wise, I like the rill marks because they're rarer. They're things that obviously occur so frequently at the present day, but they're they're pretty rare in the rock record.
Mm-hmm.
Yeah, and they're pretty. But some of the I mean, that Tumbler sandstone in Australia is full of these features in a kind of tidal environment, many of which have got very interesting kind of animal trackways on the top as well. So it adds a little bit more kind of life to the equation, which is quite interesting.
Yeah, right now living in Northumbria, I think I developed a certain sentiment towards ripple marks, because yeah, I can find them also pretty often. It's probably too much said, but I can find them sometimes when we are walking along the beach, and it just always makes me smile.
Yeah.
All right, so I think that with this, if there are no further questions, we can close this seminar. Neil, thank you very much for indeed a thought-provoking and fascinating talk. Dear audience, thank you very much for participating. And next week, there will be, yes, I'm reading it correctly. There will be no regular seminar, but we have something very special for you. And this will be SEDS Online student webinar, the second one, with the title, Influences of Sin Depositional Deformation on Sedimentation. And yes, please check all the details on our website. And also, if you feel like, please please join our coffee breaks. And yeah, thank you so much and have a lovely evening, everybody.